All right, so what I want to do next is present a solution to Maxwell's equations in a very simple case. So I'm going to say that there are no sources. That is, I mean, we basically have vacuum. So we have no charge density rho, we have no current density J. There are just no sources, it's just vacuum. What kind of solutions do Maxwell's equations admit? And you already know from previous experience that these are going to be waves which propagate in vacuum, right? So let's get a formal solution for that. Divergence of E is 0, of course, because divergence of E is equal to 4 pi times rho, and their rho is 0. There are no sources. Divergence of B was always 0. No magnetic monopoles. Faraday's law, curl of E is minus 1 by C dV by dt. Okay, that's just Faraday's law. I haven't changed that. And this is Ampere's law. So curl of B is 1 by C dE by dt. So notice that I've said J equal to 0 because there is a term related to J here. And I've dropped that in the right hand side, and I only have the displacement current, which was added by Maxwell, as I explained. So we basically have to solve these two equations, curl of E and for curl of B. You can already see that the way to solve them is to get rid of one of the quantities. So let's say I want to get rid of B. How would I do that? I have B here, but I have a curl of B here. So I'm just going to take the curl of this equation, right? So then it becomes curl of E, and then I'm going to end up with a curl of B, and I'll substitute from this equation. So what I'm basically doing is I have two coupled differential equations, and I'm trying to get rid of one of the variables in the coupled equations. So curl of E is minus 1 by C d by dt of curl of B. And notice what I've done, I've pushed the curl operator through the differential operator, right? So I can do that because all of these are linear operators, right? You can differentiate, curl is basically a differential with respect to space. That's a differential with respect to time. It doesn't matter in which order you take the differentials. The differential operator is the linear operator. So both give you the same answer. So I can push the curl inside the partial derivative with time. And on the left hand side, I have curl of a vector, and there's a vector calculus identity for it. And I've just written out the identity here. So what you end up getting is divergence of that vector. Divergence of the vector is a scalar, and the gradient of that scalar, which is a vector. So notice that the LHS and RHS are vectors, right? So any term you have here should be a vector. And so the first term in expanding out the curl of a vector is gradient of a divergence of that vector minus this operator, I think, is referred to as a Laplacian. So it operates on a vector and gives you a vector. And this operator basically gives you second partial derivative. So just like, so this operator is basically d square by dx square. So second partial derivative with respect to x, second partial derivative with respect to y, second partial derivative with respect to z. So that's called the Laplacian. So that's the left hand side. And notice that this quantity is 0 because divergence of E must be 0 because we are in vacuum. And on the right hand side, I'm just going to substitute from Ampere's law. So curl of B is substituted from Ampere's law, and we're done basically. So the left hand side is just the Laplacian operator times vector field plus 1 over c square, second derivative with time equal to 0. So first thing you notice here is if you want to work in Cartesian basis, then E has a x, y, and z component, and there's no coupling between the components, right? You can basically write out this vector differential equation as 3 scalar differential equations, one along the x-axis, one along the y-axis, one along the z-axis. They're all separate equations. There's no coupling between them in this case. So this is basically called the wave equation, the solution to the equation. I mean, there are many forms of solution. One form of the solution is in terms of complex exponentials. So here is one solution. So E is equal to a unit vector. Okay, it doesn't matter in which direction it is. It's a unit vector times a scalar, a complex scalar. So E naught is a complex number that just tells you what is the strength of the electric field. The amplitude of the number tells you the strength of the field, and the phase angle or the argument of that number basically gives you the phase angle of the electromagnetic wave. And here is a complex exponent. I is the imaginary number, square root of -1. K is called a wave vector. And so the direction of K ends up being the direction of propagation of the wave. And the dot product with R. R is just the position vector. So this is just the position in 3D space. Minus omega times t. So t is time, omega is angular frequency. So this is the most general form of the solution. Notice that I can take any linear combination of these solutions. So every time I vary E naught, every time I vary K or omega, I get a new solution. All of those are solutions to the vector equation. So, okay. So for any unit vector, any E naught, any K and any omega, you get a solution to the vector equation. Actually, one thing I need to note is K doesn't have to be a unit vector. So usually you use these hats or carets for unit vectors. So I made a mistake here. K, this should just be a normal vector. In fact, it'll turn out that in vacuum, the magnitude of K is equal to 2 pi divided by the wavelength. Okay, so what does it mean? It means that I can take any superposition of solutions of this kind, add them up, and they'll still satisfy this differential equation, right? So because I can, this is linearly separable, so I can write E as E1 plus E2, and if E1 is a solution, E2 is a solution, E1 plus E2 is also a solution. In fact, I can write E as alpha times E1 plus beta times E2, and it'll still be a solution as long as alpha and beta are scalars and constants. So that means that the general solution is basically a complex wave of this kind, but you can take any linear combination of an infinite number of these waves and they will still be solutions. So plane waves of all kinds and their superpositions are solutions to the wave equation. You can follow similar procedure. So I eliminated B here. You can eliminate E and just take the curl of this equation and then eliminate E from this equation. You could do that, then you'll get a solution like this for the magnetic field. So I've written that down here. So that's the solution for the magnetic field. And again, this works for any combination of these parameters and all linear combinations, basically. So I can take B equal to B1 plus B2 plus B3, whatever, ad nauseum. You can keep expanding it as long as each one of those terms has this form for any values of these parameters. Their superposition or their sum is always a valid solution to the equations. So that's basically the solution to Maxwell's equations in vacuum. These are all plane waves. So that's why it's called a plane wave solution to Maxwell's equations. But of course, you can superimpose a lot of plane waves with the right magnitude and phase angle between them. And you choose the phase angle by choosing the complex number here, B naught. And you can add all of them and also create a spherical wave. And the wave doesn't have to have a plane wavefront. You can have a spherical wavefront. You can have any kind of wavefront. But all of these are just waves, right? So a generic wave is a solution to the Maxwell's equation. So one thing I'm going to leave to you is or maybe I'll assign it as a practice problem, is to take these solutions and plug them back into Maxwell's equations. And when you do that, you actually learn that you actually cannot choose the constants here, B, the vector, B, the unit vector along the magnetic field, B naught, K, omega. You can choose any number, anything here, but then you're going to be tied with your choice here. You can't make an independent choice in both cases and get consistent results. So if you take these solutions and plug them back into Maxwell's equations, so you're going to show a few things. One is point A, which is that the electric and the magnetic field are perpendicular to the direction of propagation. And the direction of propagation is given by the wave vector, K. The second thing, you'll show that the electric and the magnetic field are perpendicular to each other. So they form basically a right-handed set, an electric, magnetic field, and the direction of propagation, just like the three Cartesian axes, X, Y, and Z. I will also show that E naught and B naught have the same argument. So they can be complex numbers, but their angles have to be the same. Their arguments have to be the same. And also that you'll show that omega square equal to c square times k square. So you can't choose an arbitrary k and an arbitrary omega. They are both related through what is called the dispersion relationship. So there's no dispersion in this relationship, but in general, a relationship between the wave number and the angular frequency is called a dispersion relationship. And if we have time in the course, we'll derive a few other dispersion relationships where the medium is actually dispersive. And by dispersive, I mean that different frequencies travel at different speeds. So there is actually a dispersion in the envelope of the waveform. In vacuum, of course, there's no dispersion. And so the phase velocity, which is omega by k, is the same regardless of omega. It's basically given by c. The group velocity, which is derivative of omega with respect to k, is again c. So both phase and group velocities are the same in vacuum and equal to the speed of light. So that's the solution of Maxwell's equations in vacuum, where there are no charges. So some point in the course, we'll actually come to the solution of Maxwell's equation in plasma, where you can't say that rho and j are zero, the charge and current density. We'll actually allow for a charge and current density and solve Maxwell's equations. And you'll see that you're going to get waves of a different character than these waves, but we'll come to that later in the course. So one thing which should be immediately obvious to you is the relationship to Fourier transform. So for instance, if I take this electric field, if you remember, I told you that I can basically do a superposition of a lot of terms of this form. And if you look at the form of this term, it just looks like the Fourier kernel, right? So you have e to the power of I k dot r minus omega t. So this just looks like the Fourier kernel. It looks like the complex exponent you have inside a Fourier transform. And so what I can do is I can say that my electric field is an integral over a lot of these exponents with different values of omega and k. And so basically I get a relationship that just looks like a Fourier transform. And so I kind of formalize this in the notes. So have a look at the notes which I've posted online for all the details. But the basic idea I want to make here is that we've been solving Maxwell's equations in time domain, but we can basically also do that in the frequency domain. Okay, so they're all linear equations. So anything you can solve in time domain, you can take the Fourier transform and solve the same equations in the frequency domain, and you should get the same answers. And by frequency here, I mean not just the frequency that's related to time, so inverse of time being temporal frequency, or what we generally call just frequency. It's also the Fourier conjugate of the spatial dimension. So R here is basically a position vector in 3D space. So if you think of Cartesian coordinates, then it's the X, Y, and Z triplet, which defines a position in 3D space. And you can see that the Maxwell's equation are partial derivatives with respect to space. Those are the curls, the divergences, and derivatives with respect to time. So just like you can take a Fourier transform with time, you can also take a Fourier transform along space, and k, or the wave number, is the Fourier conjugate. So k is to r as omega is to t, right? So omega is the Fourier domain representation of time, the conjugate of time. In the same way, the wave number is the Fourier conjugate of spatial position vectors. And of course, both are vectors in this case, but in time and frequency, they are scalars. So you can basically write out Maxwell's equation in a harmonic representation. And again, I have a few more intermediate steps in the notes, but I think it's already obvious if you look at the exponent we have here. If I take a partial derivative with respect to time of E, it's one of the terms in the Maxwell's equation. So if I want to actually represent this term for this solution, I take a derivative with respect to time. The right-hand side remains exactly the same, times minus I omega, right? So you can use the chain rule. The exponent, the derivative of an exponent is the same exponent times the derivative of the argument of the exponents, that's minus I times omega. So if you look at a partial derivative, you can replace that operator. So I'm thinking of this in terms of an operator. I can replace the differential operator in the Fourier domain with a multiplicative operator. So differentiating in time is like multiplying by I omega. again, differentiating with respect to space is going to end up being multiplication by I times k. And of course, I've kind of written it in an easy form here, but k is of course a vector. So this applies to each component of the vector. And when you write all the components out, which I do in the notes, you get that the divergence operator is just a dot product with k. Okay, a divergence of a vector gives you a scalar. A dot product of k with a vector will give you a scalar. And again, you can show that a curl operator becomes a cross product with k. And so you can write out the Maxwell's equation in Fourier representation, in harmonic representation. Gauss's law just becomes k dot e. The divergence is just a dot product equal to 4 pi times rho. Divergence of b equal to 0 is just k dot b equal to 0. Curl of e again becomes k cross e. And the time derivative becomes just a multiplication with minus I omega. And similarly with Ampere's law, curl of b becomes k cross b. And again, you can take all of these and again solve, to get the wave solution. And remember, we took curl of Faraday's law and substituted from Ampere's law. And now we're just going to take k cross of Faraday's law, and then substitute Ampere's law in it. And again, you end up with this equation, and that is again an equation for a wave. This equation is basically the wave equation in Fourier domain. And I want to introduce this formalism, even though I won't take it further here, because this formalism will become extremely easy to apply when we actually try to solve for the wave equation in plasma. It just becomes easier algebraically to do it in the Fourier domain, to get an equation of this form and then find the properties of the electric field E which satisfy this equation in a plasma, and then that's how you'll get to the dispersion relationship in plasma. So we'll do that as a practice problem, but just be aware that sometimes the algebra is simpler if you just do it in the Fourier domain. If you're uncomfortable with curls, divergences, and all of that, and you just want to convert that to vector algebra, then just go to the Fourier domain. Curl becomes a cross product, divergence becomes a dot product, and things are, in a certain way of thinking, things become simpler. Okay, so another point which I want to discuss here is energy conservation. And every time you encounter a new force, you need to ask yourself, well, what is the energy conservation that applies to that force? So every force must have an energy conserving principle associated with it. And so we spoke about Lorentz force, and the question becomes, okay, what is the energy conservation which undergirds all of these Lorentz force, the Maxwell's equations, and all of that? There must be some energy conservation law. So we can actually work through that by just calculating what is the work done on charges by fields, right? So we have a force. The moment you have a force, you can define what is the work done. So force dot product with displacement is the work done. So I've just chosen to work with the volume density form instead of a single charge of the Lorentz force. So that's the force per unit volume. The work done per unit volume is that force times the dot product with the displacement vector ds. So I've just taken a dot with ds of this equation. Now the interesting thing here is j cross b dot ds must be 0. And the reason for that is the force is always perpendicular to the displacement in a magnetic field. So the magnetic force leads to a displacement that is always that's always perpendicular to the force itself. And you'll actually get to this result formally when we actually solve for cyclotron motion. So we'll do that in class. We'll just solve the dynamics of a charge in an external magnetic field, and you'll see that the force is always perpendicular to the displacement. So in that case, this term goes to 0 because you're just taking a dot product of two orthogonal vectors. That goes to 0. And so you end up with work done per unit time per unit volume element. So I'm just going to divide that by dt. Sorry, there shouldn't be a vector on t here. T is a scalar. So again, you get the work done per unit volume per unit time. And ds by dt is basically the velocity, right? So f dot v is basically the rate at which work is done. And so you get E dot ds by dt, and ds by dt is basically the rho times ds by dt is basically rho times the velocity. Ds by dt is velocity, rho is the charge density times velocity is the current density. So E dot J is basically what we are after. E dot J is the volumetric rate at which work is done by the fields, the electromagnetic fields on charges. Okay. Now, so we can kind of plug in Maxwell's equations into this, and then we get a very nice result called the Poynting theorem, which is basically a statement of energy conservation in electromagnetics. So remember, from Ampere's law, I can solve for J, and that's just the curl of B. That used to be the term on the left-hand side, but I've just taken J on the left-hand side, and this is Ampere's law. And I'm going to substitute for J here. So J dot E is equal to, I'm going to substitute for J from Ampere's law. So I have the first term here is curl of B and dot with E. I'm doing J dot E. So curl of B dotted with E minus the second term here is basically dE by dt dotted with E. Okay, so dE by dt is a vector which is parallel to E, and I'm basically dotting that with E. So I'm dotting two vectors which are parallel to one another. And so when you dot two vectors parallel to one another, the result is basically the square of the amplitude of the vector. So I'm just going to write this as E here. This is just the square of the amplitude. And so when I take that inside the derivative, this derivative is equal to 2 times E times dE by dt. So to account for that factor of 2, I've put 8 pi here instead of 4 pi. So the extra factor of 2 comes from differentiating E square. Okay, so now this term can be expanded again. So you expand this term by using another vector identity, which is A dot curl of B is B dot curl of A minus divergence of A cross B. So let's see what happens when you plug that in. So this term remains the same, and I've now expanded out the dot of a curl here. Again, you can pause this video, and I want you to all to work through it yourself, do the derivations yourself, but use this video as a guide. But to really understand the derivation and what's really happening, you need to work it out yourself. Okay, so let's look at the terms here. So this term is B dot curl of E. And this term is divergence of E cross B. So we're going to keep this term as is because we can't reduce this any further. So we're going to keep this term as is. Now, curl of E, I can basically get rid of this using Faraday's law, right? So curl of E is minus 1 by C dB by dt. So I've just substituted minus 1 by C dB by dt from Faraday's law. And again, I end up with a term which is B dot derivative of B with T. So again, these two are parallel vectors. I'm dotting two parallel vectors. So again, I can write that as, a time derivative of a scalar B square. So B is just the magnitude of the vector. So you get a term over here, which is, partial derivative of B square, which is just, very similar to the partial derivative of E square. You pull that together, and this is the final form. So this is called the Poynting theorem. So let's see what it's telling us. On one side is the volumetric rate of work done by the field on the charges, right? So this is the amount of work done by the field on the charges per unit time, per unit volume. That is what J dot E is. Now let's look at these two terms. So this term turns out to just be the rate of change of energy stored in the electromagnetic field. So B square by 8 pi plus E square by 8 pi is the amount of energy stored in the electromagnetic field itself. So what do you mean by energy stored in the electromagnetic field? Well, to create an electromagnetic field, you need to assemble charges, right? So you can think of this as the binding energy of the electromagnetic field. Just like the gravitational field of any object has stored energy in it, the gravitational binding energy, the electromagnetic energy itself is analogous to that. So to create an electromagnetic field, you need to have a charge arrangement. You need to arrange the charges, and the work you do in arranging those charges is stored in the electromagnetic field generated by the charges. So B squared by 8 pi plus E squared by 8 pi is the volume density of the electromagnetic energy. So it has units of ergs per cubic centimeter. It's the amount of energy per unit volume. And of course, there's a time derivative. So this is the rate of change of energy stored in the electromagnetic field per unit volume. Okay, so what's this term? So this term is the Poynting term. So C by 4 pi times E cross B. So this term without this gradient is called the Poynting vector. And notice that E cross B in vacuum is in the direction of propagation. So the Poynting vector is pointing in the direction of propagation, and you're taking the gradient of the Poynting vector. So this term is the amount of energy that the fields are radiating away. So the fields are carrying away with them. And that is called the Poynting flux. Okay, so once you take the, so C by 4 pi times E cross B is called the Poynting flux, and the divergence of that. So the amount of Poynting flux which is going away from a point is the divergence. So that is the amount of energy that is being radiated away from a point. So that's the differential form, right? So what it's saying is that there is there's a net energy conservation. The energy goes into doing work on the particles. The energy is stored in the fields itself, and energy is also being radiated away from a point. And those are the three terms, and they all have to be in balance. So if you want to increase one, you need to decrease the other, and vice versa, such that when I add all three of them, I should get zero. That means that energy is conserved. If you remove energy from the fields, then you have to either use that energy to do work on the particles, or you have to radiate that energy away, right? And so if you're radiating energy away, then it has to either come from the energy stored in the fields themselves, or it has to come from the charges, right? So the charges have to do work on the fields to radiate them away. And so basically, in a nutshell, this is energy conservation in the electromagnetic field.